All right, class, so this is the second sort of practice problem that I gave you, and this is a pretty tricky problem. There's a lot going on here, so let's get into it. And in this problem, we're asked to determine the final pressure inside of a sealed reaction chamber if the chamber is originally loaded with 2.44 atmospheres of N2 and 6.32 atmospheres of H2. You can assume the volume and temperature stay constant. So if we want to sort of draw a sort of crude picture here, we might say that that's my reaction chamber. It's sealed. It's got a certain volume and temperature that stay constant. So you could say it's insulated. And then inside, we're going to put that N2 plus H2 gas mixture. So the gas molecules will be moving around in there. And then as they're moving around, what's different about this problem, or what's difficult about this problem, is that they're going to react to form NH3. So the first thing that we need to sort of consider is how much N2 do I have and how much H2 do I have, and is there going to be a limiting reagent? And in this case, yes, there will be. So there's a number of ways to solve a problem like this, and I'm going to show you sort of the less elegant way first, the way where we're just going to sort of make some assumptions and do a whole bunch of calculations to solve the problem, and then I'll show you a more elegant way at the end of the video. Both give you the same answer, obviously, but one's, well, you'll see. So the first method 1, is going to be to assume standard temperature and pressure, or not pressure, but standard temperature and 1 liter of volume. So we're going to say we're going to assume 1.0 liter volume and 273 Kelvin temperature. And these doesn't really matter what you choose, right? But we're going to make those assumptions, and then what we're going to do is we're going to solve for moles of N2 and H2. So we're going to say, well, let's just assume that we have this condition, and we've got different partial pressures of N2 and H2, and we're going to use those to solve for the moles of N2 and H2. So if we go ahead and do that, the calculation for N2 will look like this. We'd have 2.44 atmospheres times our 1 liter equals N moles of N2, our R value, and then our temperature of 273. And N2 is equal to 0.109 moles of N2. So essentially that's how many moles of N2 gas we have in there. We'll do the same thing for H2. Now my pressure is 6.32, everything else is the same. .273, and our moles of H2 now we can calculate are 0.282 moles. Now we need to do a limiting reactant problem. We need to figure out which one of these is going to be the limiting reactant. So each one of these reactions takes 1 mole of N2, but it takes 3 moles of H2. So I'm going to need essentially 3 times as much H2 as N2 to do this reaction. So if I want to quickly figure out what the limiting reactant is, what I would do is I would take 0.282 and I would simply divide that by 3. I'm going to divide that by the coefficient, and that's going to tell me sort of the number of reactions that I could do, but it's also going to give me a lot of information about which one of these is the limiting reactant. So what this is telling me, 0.094 moles, this is telling me essentially how much N2 I would need in order to do this reaction. We can see that I'm going to have excess N2. So this is going to tell me that H2 is the limiting reagent, and that at the end of this reaction, I'm not going to have any H2 left over. There's going to be no H2 left over. All of this H2 is going to be converted into NH3. I am going to, however, have some N2 left over, and we're going to have to take that into account in just a minute. So the next thing that I would do is I would say, okay, well, if this is my limiting reagent, and I've got 0.282 moles of H2, how much NH3 am I going to form? 2 moles of NH3 for every 3 moles of H2. So this is going back to our stoichiometry from General Chemistry 1. And this calculation is going to tell me that 0.188 moles of NH3 are going to be formed. So this is my number of moles of NH3 that are going to be formed. And this is going to tell me sort of what the pressure is going to be, and once we do one more calculation. But 0.188 moles of NH3. Now I want to know what the N total leftover is going to be. So N total leftovers, that's going to be the moles of NH3, but it's also going to be some moles of N2 left over. So we need to figure out how much N2 is left over. So if I want to go back to this calculation here, this is telling me that 0.094 moles are going to be consumed, right? That's how many moles of N2 I need in order to do this reaction and react all the H2. So 0.109 minus 0.094, that's going to tell me how many moles of N2 are left over. So minus 0.094 moles consumed, right, equals 0.015 moles of N2 left over. So I need to take this moles of N2 into account. So my total moles is going to be my moles of product that I formed, moles of NH3, plus my moles of N2. So my total number of moles is equal to 0.203 moles of gas. So in total, I've got 0.203 moles of gas in this reaction. So now, using my same volume and temperature, because those haven't changed, I can solve for my P total, 1.0 volume. Now I've got 0.203 moles of gas, 0.08206 R value, and then 273 again. And I can solve for my pressure, and that equals 4.54 atmospheres. So that is my final answer. Now there's a much more sort of elegant, quick way to get to the same exact answer. The way that we would do that is just sort of draw a little aside here. N2 gas plus 3H2 gas goes to 2NH3 gas. And we're starting with 2.44 atmospheres and 6.32 atmospheres and 0 atmospheres, right? So that's our initial conditions. And then this reaction is going to go and we're going to form some NH3. Now, since we are holding volume and temperature constant, then the pressure and the number of moles are going to be directly proportional, meaning that I can treat essentially these 6.32 atmospheres sort of as the number of moles that I have. I can treat it in the exact same way, really. So again, I could figure out that this is going to be the limiting reagent, right? Because the pressure is, again, directly proportional to the number of moles. So if you take 6.32 and you divide that by 3, that's going to tell you that you need to have 2.1 atmospheres of N2 in order to consume all of that 6.32 atmospheres of H2. So we have 2.44, we only need 2.1, so this is going to be our limiting reagent. Using that same sort of idea, I can figure out, well, how much N2 is going to be left over? Well, if I have 2.44 atmospheres and I'm going to use up 2.1 atmospheres, then 0.333 repeating atmospheres of N2 will be left over. So the next question is, how much H2 will be left over? Well, 0, right? It's a limiting reactant, so there will be no leftover H2. And then the last question would be, how much NH3 is going to be formed? So 6.32 is my limiting reagent. And then I can do my mole-to-mole ratio. 2 moles of NH3 are going to be formed for every 3 moles of H2 that are consumed. Therefore, 4.21 mole atmospheres of NH3 are formed. So if this is my partial pressure of NH3, this is my partial pressure of N2, I'm just going to add those together. 4.55 atmospheres. So I think depending on your rounding, so here I've got 4.55, looking at my rounding here, and depending on how you round this, you should get the exact same answer. So probably a little rounding error on my part over here, but 4.55 should be the same pressure that we get for both methods.